Hello, class. My name is Isaac Joseph. Today I'm going to be talking to you about my Project 1 for Engineering 360.
So let's get right into it. This is going to be our question that we're working on today. We are given a random variable as a function of another random variable and a discrete function over here. So we can see right off the bat that this L function or L random variable is going to be a mixed random variable, and I'll explain that in just a second. We can say right off the bat that this is going to be a mixed random variable. And we can say that because we can identify very easily that this mixed random variable, L, is a summation of our continuous random variable here. So this is our continuous part, and this is our discrete part. So we can see that looking at the graph over here, which is going to be a graph relation of L being on the y-axis and V on the x-axis, that we have our continuous part here, which is linearly related between L and V, and we also have our discrete parts here and here. The probability that L is equal to 0.5. But looking at our graph over here that we've constructed from the equation given to us in the question, we can see that L is equal to 0.5, where L is our x-axis, whenever our V is going to be between this range right here, and whenever our V is going to be between this range right here. Now pay attention here because at this point, L is not actually equal to 0.5 because we have a discontinuity here. L is actually at this point going to be equal to negative 0.5 because of our relationship here where when V is equal to negative 0.5, L is actually going to be equal to V. When we are looking at the probability of L being equal to 0.5, we can say that that is the same as the probability of V being between negative 1 and minus 0.5. But notice that it's not equal to minus 0.5 here because of this jump. And in union with that, we're also going to, it's also the probability that V is going to be between 0.5 and 1. The voltage V is a uniform random variable. So, given that, we know that V is uniformly distributed over this period of negative 1 to positive 1. So, because of that relationship that we're given, we know that we are able to, in order to find the probability of this region's occurrence and this region's occurrence here, length of the region here, and divide it by the total region in order to find its probability. So the probability of each of these in union with each other is going to be 0.5 over 2 plus 0.5 over 2, which is just going to give us a probability of 0.5 or 50%. So the CDF is going to be our cumulative distribution function, which is capital FL of little l here. And this is defined as the probability that L, the random variable, is less than or equal to little l, or its value at a point. Looking at our L values here on the y-axis, let's first talk about our region when L is less than negative 1/2. So in this region here, this is going to be our first analysis. We can see that actually looking at our graph, that L is only between minus 0.5 and positive 0.5. So the CDF below minus 0.5 is going to be 0, since L never occurs less than minus 0.5. Let's go on to our second region here, where we talk about L being between minus 1/2 and 1/2. We're talking about the values of L here that are going to be between minus 0.5 and 0.5 over here. So this is going to essentially be the span of our graph, but we are not going to be including 0.5. In this span, we're actually talking about this linear region that we have right over here. So this is going to be our linear region where in this region, you'll recall L is going to be equal to V. What we can say is that the probability that L is less than little l or equal to it is the same as the probability that V is equal to or less than little l, since L is equal to V. So what we're going to do is we are going to take the integral here of our V function over here. We're going to integrate between our limits, which are going to be minus 0.5 to L. Let's say we're going to represent it right here, and it can be essentially moving anywhere from negative 0.5 all the way up to, but not including 0.5, to find that our 1/2 is a constant, and the integral of dv is just v. So we integrate v from L to 0.5, and we find that the CDF of L in this region is going to be this right here. So, and we're going to check out our last region over here, which is when L is greater than or equal to 0.5. So Before we were only talking about all the values below here, but now we're talking about from 0.5 and anything else above it. So we can see that L is only equal to 0.5. It's not equal to anything above 0.5. But when we're talking about the CDF, we're talking about the probability that L is equal to or less than little l. So in this case, we're going to be talking about whenever L is at 0.5 or above it. So the probability that the random variable L will be less than or equal to little l, well, in this region over here, everything is covered because everything is going to be less than or equal to 0.5. So we can say that the CDF of this region is going to be 1. So we can graph this as well, and we can see that when L is less than minus 0.5, it's going to be a 0 here. When L is between minus 0.5 and 0.5, it is going to be a linear relation between this CDF and our L value over here. This axis is going to be L, so this is going to be a linear relation right here, and we're going to have in discontinuity a little jump over here, so you can see an open circle, and then when L is greater than or equal to 0.5, the CDF is going to be 1. So here is where this jump is going to end up, and we are going to have our discrete section. So you can see again that we have another instance where this random variable, the CDF, is also going to have this discrete region, another discrete region, and then this one continuous region. So our final part of this question is to find the probability density function of our random variable L. So our probability density is going to be little f of L at little l. And our PDF, our probability density function, is going to be the derivative of the CDF. My terminology that I'm using in my representation was probably not the best, but what I meant by that was the only non-discrete region that we had, because as you can see, this region, the value of the CDF is constant, the value of the CDF is constant, and this region over here is when it is our linear region. So we're going to take that linear region on our CDF, and in order to find the PDF at that region, we are going to take the derivative of it. So this is our value of our CDF in this region right here. We're going to take our derivative of this, and with respect to L, and we're going to find that we have a value of 1/2 of our probability density function being located at that region. And then we can see our other region again is when little l is going to be equal to 0.5, because at this region we are not equal to 0.5 once again, so it does have a jump here, and we're going to find our PDF at that point, which is just going to be 1 minus the probability density that we had already calculated for our other region here. So this is going to give us another 1/2. And we can see once again that from the definition of a PDF, that the f of L with respect to little l is going to be equal to the probability that L is equal to little l. And so we can verify this answer that we got here by saying that our answer that we had solved in the first part of this problem, which was that the probability that L is equal to 0.5, is actually going to be the same as this value that we've just calculated, which is correct, because we are looking for, in this instance of the PDF, the probability that L is equal to little l, where our little l is 0.5. So that is our way that we can check this, and we have our PDF function here represented, and we have our PDF graph. Our PDF function is going to be this piecewise function where we found it's 0.5 between our on our continuous region. It's 0.5 at 0.5 is equal to L, and it's going to be 0 otherwise. So we can see that it's going to be 0, and it's going to stop being 0 and have this jump up to 0.5, and it's once again going to continue on being 0 above 0.5. So this is our PDF of this function, and we have solved this question, and I hope you guys enjoyed this video, and thank you very much.